Hi, I'm Justin Hensley. I'm a senior member of technical staff in AMD's Office of the CTO, where I work in advanced technology initiatives. So this is part 4 in a series of videos about OpenCL. So just to give you an overview of what we're going to be talking about in this video, video 4 is kernel execution. So in particular, we're going to be talking about execution and synchronization of kernels. Recall from previous videos, we've talked about program and kernel objects. So program objects encapsulate the program source or precompiled binary from disk, a list of devices, and the latest successfully built executable for each device, and a list of kernel objects. Our kernel objects encapsulate a specific kernel function in a program, and it's declared with the kernel qualifier, and also contains the argument values for this kernel. Kernel objects can only be created after the program has been built, so you can't just create a kernel object without first creating a program object. So let's start. Let's say we have a program object here. So the first thing we're going to do is we're going to have some kernel code. So that's shown on the left. We're going to take that kernel code and we're going to compile it for the GPU, and that'll give us GPU code. But let's say we also have an OpenCL device that is using the AMD CPU. In that case, we'll have to compile it for the CPU, and we'll get x86 code for that. So we'll have two different kernel objects, two different kernel binaries, one that'll run on the GPU and one that'll run on the x86 CPU. Programs build executable code for multiple devices. So the key point here is that you can have the same high-level code run on multiple different devices, because at runtime we can compile the code for the devices that we have at runtime. So you could even have a system where you have any number of these devices compiled for. So you could have a GPU in the system, x86 CPU, and even a DSP. So you would have 3 different sets of code in that situation. Let's look at how we can compile kernels. So first we create a program. So the input is going to be a string, so source code, or a precompiled binary that we've loaded from disk. So you can kind of think of this as a dynamic library. It's a collection of kernels. We have multiple functions we can call into this program object to do certain tasks. So let's say we're doing image processing. We might have something that would scale the size of the image, rotate an image, transpose an image, or any sort of image operation. So once we've created that program object from a binary or a source, we're going to compile that program. So we're going to specify the devices for which that kernel should be compiled, and then we're going to pass in compiler flags. OpenCL has a standard set of compiler flags, and then the specific runtime you're using might have additional runtime flags. So this might be the level up to optimization you want the compiler to use, what kind of floating point math you want it to use, etc. You can also use this to check for compilation errors. So let's say you're just testing out a program that you just wrote. You could compile it, and then if it returns with an error, you can get a build log back that'll tell you the specific errors of your kernel that you tried to compile. Once we've done that, we're going to create some kernels. So we've created our kernels from a built program. We're going to get a kernel object, and that's going to hold the actual arguments for execution and what we actually send to the different OpenCL devices to execute. So once you've built and compiled your program objects, you need to actually create the kernels. So this is going to return a kernel object used to actually hold the arguments and the actual executable that'll be run on the different devices. So the first thing we're going to do is we're going to create a program object that is a CL_program. And then we're going to create program with source. So we have a context that we've created previously. We're passing in one set of source files, and we have in this case, we're not giving it any compile flags, so we're saying use all default compile options, and then we get our error back in the error field. Compiling and creating a kernel. So once we've taken that program object, we've built it, and now we need to create a kernel. We're going to build a program as we did before. And again, we're passing in program, and in this case, we're just using all the default arguments because for this simple example, that's all we need to use. And then we'll check for our error. And this is actually showing us how we can actually get the build log. So we're going to use the CL program build log flag to let us get back a log of what happened when we built. So if we actually had an error, we could get back this build log, and it would tell us all the information about where it failed when it tried to build this program. So in this case, we're going to simply do a CL create kernel. So we're going to take our program object that we just built. We're going to tell it we want the average image kernel, and then we'll have an error flag. So we'll create a kernel object from that single kernel instance that is in that program object. Now that we've actually compiled our program objects and created our kernel objects, we actually want to execute our kernel. So there are 2 basic steps in executing a kernel. The first thing we need to do is set the kernel arguments, and the next thing we'll do is enqueue the kernel. So let's look specifically how you would set the kernel arguments. So to set the arguments, we're going to use the function called CL set kernel arg. And in this case, the first argument is the kernel that we care about. The second argument is we need to tell it the index of the argument we want to set, the size of that argument, and then the actual argument. So in the first case, we're telling take kernel object named kernel, set the 0th argument with the size of input to the value input, and then we're going to set the output the same way we did with the input, but instead we'll say set the output. Then we actually want to execute it. And so in this case, we're processing on images. So in this case, our n-dimensional domain will be 2. So you'll notice that we have our global size there set to image width and image height. The third argument we don't really care about because in the next call, we're going to tell it we're only doing 2D operations. So in the next line, we actually enqueue the work, and we use CL enqueue ND-range kernel to actually enqueue the work. The first argument is the queue, so that's the particular queue we want to enqueue work to. The second argument is the actual kernel that we're enqueuing. The third argument in this case is the actual global domain size. So in this case, again, we're doing a 2D image, so we're going to tell it 2. The next argument we're not going to use. And then finally, the next argument is global, and that's actually the size and width and height of our domain. And we're passing in the width and height of the image that we're processing. The rest of the arguments are default for this simple case. We'll talk a little bit more about events later, and that's when we'll be using those last arguments. So here we note that we're executing our kernel asynchronously because I'm not passing in any events. So from previous videos I talked about you need these events to actually synchronize your kernels. In this case, you're just requesting the OpenCL runtime to enqueue that task into a queue that will later be run. So nothing may happen. You might actually make this call and then it might take the runtime a while to actually get to the point where it can execute that kernel. You've only enqueued the kernel. You need to use something such as a blocking read, and that would be a CL enqueue read with an argument of true with for the blocking argument. And when you use that, that's one way of forcing the runtime to flush everything and force the kernel to actually be executed. Again, though, when you do this enqueue, it is not executed right away. It's done asynchronously. Another way of doing it is you can use events to track the execution status. So the reason you'd want to use events to do this is that allows you to have your host running your host application not block on OpenCL calls. So you could actually multitask that way. So your host application can enqueue work, go off and do something else, and then come back and check to see if an event is done. And if the data is absolutely needed, it can force the runtime to return with the data once it's ready. So let's say we want to synchronize between commands. So each individual queue can execute in order or out of order. So for an in-order queue, all commands execute in order as you would expect. And this behaves just as you had expected, as long as you're enqueuing from one thread. Things can be more complicated if you're enqueuing from multiple threads on the host side. You must explicitly synchronize between queues. So let's say you have multiple devices. So let's say you have an OpenCL device that you're using on the AMD CPUs, and you have another OpenCL device that you're using on ATI GPUs. So you're going to have two different queues, each with one queue to those devices. And you have to use explicit synchronization between those queues. The way we do this is we use events. So there are commands that return events and obey a waitlist. So every command, you can give it a waitlist to say, wait on these events. And they also return an event that tells you, this is the event ID that I use. So any of the enqueue commands will take in 3 different arguments. So the first of the arguments is a number of things to wait on, and then a list of those events to actually wait on. And the final argument is the event that that command creates that you can further use in other commands to do synchronization. So let's give a simple example where we have one device and one queue. So in this case, kernel 2 is going to use the result of kernel 1. So with one queue, we're going to enqueue kernel 1 at some time point. It's going to go into the queue, but it's not going to necessarily execute as soon as we enqueue it into the queue. But we can also enqueue kernel 2 right away, and that's because these are asynchronous calls. So they return right away as soon as you call them. So we'll enqueue kernel 2, but it's enqueued in the queue, and it's not going to execute until after kernel 1 is executed because we have a single in-order queue. So after kernel 1 finishes, kernel 2 then be executed on the GPU, just sort of exactly how we would expect it because it's a single in-order queue. So let's talk about a slightly more complicated example. So let's say we have 2 devices and 2 queues. So in blue we have kernel 1, and in purple we have queue 2. So in this case we're going to have kernel 1 running on the GPU and kernel 2 running on the CPU. And what's going to be a little bit different about this is that kernel 1, which is running on the GPU, is going to output some data. That's going to be input into kernel 2, which is running on the CPU. So there is an explicit dependency here. Kernel 1 must finish before kernel 2 starts because the data from kernel 1 is going to be used in kernel 2. So let's look at how this would happen if we didn't use events. So notice we'll have two queues here. We have two devices and two queues. We have one queue for the CPU and one queue for the GPU. So we're going to in-queue kernel 1 on the GPU's queue. It'll go into the GPU's queue and sit there for a little bit. And then at some point after that, we're going to in-queue kernel 2, and that'll go into the CPU's queue. So at some point, the runtime will decide it needs to in-queue on the GPU kernel 1. But simultaneously, it might actually decide that, hey, I can in-queue kernel 2 on the CPU because the CPU is free. So if we don't use any synchronization, what will happen is kernel 1 and kernel 2 will be executed at the same time. Clearly, that's not what we want, because kernel 1 is producing data that kernel 2 needs. What we really need to do is we'll in-queue kernel 1. Kernel 2 will wait until kernel 1 is actually done. Once kernel 1 finishes, we can then have kernel 2 actually start executing on the CPU. And that way, we can ensure that the data produced by kernel 1 is then used by kernel 2. So this is where we use events. So the events tell the runtime which kernels need to wait on other kernels. Besides actually using events to manage kernels that are run in our queue, we actually might want to manage these events from the application. So this allows the application to actually further optimize and use resources as much as possible. So in this case, there are a couple ways we can use events on the host application. One is the CL wait for events call. And that's pretty simple. It just takes in a number of events to wait and a list of events to wait on. So what's going to happen is when you call this, the host application will wait and block until all events in that list are completed. Another interesting thing you can do is you can in-queue a marker. So this allows you to put a marker into the queue that you can use to track how fast things are moving through the queue. So when you're doing optimization and performance testing, you'll be able to know when certain things are happening. Another option is to in-queue wait for events. So this is similar for wait for events, except what we're doing is we're in-queuing this into the queue system so that the OpenCL runtime itself will block. So the nice thing about this is that it allows your application to go off and do something else, but still have a point at which you know the OpenCL runtime has reached a certain point, but you're still not blocking on that application. Finally, there's also the CL get of info. And so this will tell you command types and status. So you can ask for a certain command, has it been queued? Has it been submitted? Is it running? Is it complete? Or is there some error code? So this gives the application, as you're doing more and more optimization, to know exactly what's going on. And the last thing I want to talk about on this slide is that CL get event profiling info. So this gives you basically command queue, submit, start, and end times. And what this allows you to do is actually profile your application so you can figure out what kernels are taking the most amount of time so you can further optimize those kernels as needed. So this has been video 4, and I thank you for watching. This is Justin Hensley.